All right, welcome back. So today we want to look at Numpy fundamentals as we continue our learning in machine learning with Python. When it comes to machine learning, Numpy is a very important aspect of machine learning because majority of data that we'll be dealing with, some of them comes in form of array of data. Some of them are matrices of data, especially when you are dealing with those kind of genetic data, like gene expression, the rest of them. So it is important to understand the concept of NumPy, but it helps you to manage your data. It is actually means NumPy means numerical Python. It's the foundation package for numerical computing in Python because it provides efficient n-dimensional arrays. We call it ND arrays. It is the fast mathematical operations on arrays. It's a tool for linear algebra, random number generation, and so on, and a seamless integration with Pandas, Scikit-learn, and TensorFlow and PyTorch. All right, so why do we need to look at it, NumPy for machine learning? Because it handles large data set efficiently, faster than the list. It optimizes for vector or matrix operations. Any kind of matrix-based, vector-based is the key for ML machine learning algorithms. It's used internally by Pandas, Scikit-learn, and deep learning frameworks. So if even without you explicitly handling it internally, you already have the operations to handle all those things. So for data representation, we use ending array for all numerical data, such as images, tabular data, and so on. Okay, so I'm going to look at how to start declaring, creating an arrays. Arrays come in creating of array in different languages are not the same. In Python, it's very easy. It's handled majorly by NumPy. Okay, we have one-dimensional array, right? So we have to import our NumPy as usual to handle it. So which means just one array straight in a matrix form or in a vector form. So we have NPy array. So just put the data inside the vector and to form a NumPy array. So you can actually print it out to give you the list of data that you put inside. We have the two-dimensional, which means you have in two forms, matrices now. So we can declare another one here. You can do np.array, create the second one, put them in brackets together. So it become two set of data. This can be a huge data, but you're just using 1,2 to represent it, and similarly to this one also. So it can be a data set and that old data set and trying to work together. So just a simple example. We have some special arrays. All right, we have zeros, which means enter the zeros, which with 2,3, which we can pass in 2,3s. So it means 2 by 3 matrix of zeros, just only zeros. Okay, we have 2 by 3 can be 2 by 2, 3 by 3, but this one you are looking at just create 2 by 3 only, can be any kind of dimension initially, but they are all zeros. We also have ones. We call it ones. np.ones 1,5 means 1 by 5 vectors of ones, only one throughout. Maybe you want to create an identity matrix, for example. I just use this one to create identity matrix, the 2 by 2 of ones. Okay, so it gives you your answer. So we also have what they call array range. This array range, we call it array range. So it means that you have to start by starting from 0 to 10, 2. Now, when you're dealing with n range, it has a different kind of operations, because it will give you, it is a 0 to 10 minus 2, because if your step value is 2, it means 0 to 10 minus 2. This 2 means that it is the step 0, 2, 4, 6, 8, as I put it here. But what I'm trying to emphasize here is that this particular 10, it will not reach 10, it will only reach 8 and stop. So that is what n array. So what it does. So when you are declaring, just mean that if you are using step 10, it will count. It will stop if a number before the number you put there here. So to count one backward. That's what it means. All right. So you can actually print out all this one I put. You can print them out. For example, you want to print this one out. For example, maybe can you supply maybe print can you say print maybe which one should we print now? Let's say print range. So we can just give us our values. So we have a 0, 2, 4, 6, 8. So any of them can be printed out as you want. You can print out maybe if you want to print maybe one once, for example. Just print one value, you can see. So and so on and so forth. So if I have changed this one maybe to 1, or maybe 2, 2 for example, or 2, 3 for example. So I could have printed it out as well as once, because you see 1, okay, I see. So this is just a identity matrix, for example. So that is how it look like. All right, so let's look at array operations. As you perform mathematical operation on other data, so you can also perform on arrays as well. So let's say we have a equals to n, and we declare another array as assigned to a, another array assigned to b. So you can do it element-wise operation by adding, can print a plus b, which means we are trying to add this and this together. Okay, this plus this, this plus this, this plus this. So it give us a 5, 7, 9. Right, so we can also multiply two of them together. 4 times 1, 4, 2 times 5, 10. I mean, we can say that okay, we have okay, this one is by 2 now, multiply by 2. So we can have 2 times 1, 2 times 2, 2 times 3, which is 2, 4, 6. All right, so that is what we have. So if you print them, we add what you get. You can also do what is called dot products. This one is common in linear algebra. We are dealing with vectors, what they call dot products of vectors. So in that case, we can multiply, and as you are multiplying, you are adding, which means we are trying to do that this times this plus this times this plus this times this. That's called dot product. So if you run this now, we are going to have 32. That is dot products. Then you can also have what they call inverter functions, normal function you perform in mathematics. You have like a square root, exponential, sine, cos, tan, and so on. You can so declare them here. So you can just supply np dot square root a, give you your answer, np dot exponential a, or b, whichever one you want to use. You can declare them there. So we print them out for you. So if you run this now, you have the values supply here. As you can see 32. You can see here this one as well here. So print them out for you, right? Square root of a, as you can see. Also print your exponential of a. Also print sine of a. You can see each of them here. So this is for only for a. You can do for b as well if you want. So this is just a sample of performing mathematical operations on the NPy array. Alright, so you can also reshape an index. Okay, you can say okay, let's let's first create a matrix first. Create a matrix of 3 by 3 first. This is a np.arrange 9.reshape 3 by 3. This 3 by 3 matrix. So if you print this out now, for example, if you say okay, print matrix, for example, to print out this for us 3 by 3 matrix of 0 to 8. Okay, don't forget I told you last time that matrices in Python or index in Python actually begins from 0. Okay, so forget that. So it counts from 0, 1, 2, 3, 4, 5, 6, 7, 8. So it stop at 8. So you have 9 numbers inside. That what it means. So don't forget that. So you can print all the matrices out, or you can say you want to print part of the go to index or the shape. So you can just say okay, print a second row. Don't forget the first row is 0. Okay, don't forget that. So the same thing with column 0, 0. So second row, that's 1, comma, then all. Second row, it means all columns for second row only. Okay, second row. Let's first print our matrix out. I think let me see if I can. Okay, don't worry, we print everything together later. So print matrices. We have all columns, for example, here, but we want to select here. I mean all like that, all rows rather. Sorry, all rows. They want to print select for columns 1 to 2. Don't forget, because it begin from 0, 1, 2. 0, 1, 2 means 3. So if you have 3, 3, semicolon 3 here. So we are taking okay, from 1 to 2. So don't let that be confusing for you, because that is just a Python method. So it's not the same way in some other language. The majority of the language begin with 1. The pattern begin with zeros. So that is what primarily confuse many people. So, but after some time, you get used to that. All right. So we have 0, 1, 2. So that is a 1 to 3. All right. So you can also have a npy declare in two variable forms. We have one set, another set, which we have seen other time. So you can also combine them together. All right, if you want, you can say okay, print this particular array 1 to 2. So these are combined two forms. Now we have a we are going to print. Okay, can you give us 6, which means a second row, third column. This one is second row. Row comes before columns. Row by column. So second row, third columns. Right. So don't forget the method start from 0. Then same thing applicable here. We want all rows here, but only the second column, right? So which is a 0, 1, second column here. So this is just a technique of matrices and shaping in R. So if I run this now, I will have all my data. This is the matrix. It's a 3 by 3, 0, 1, 2, 3, 4, 5, 6, 7, 8. That is the matrix, printing the matrix out. Then second line, now printing for me second row, which is this one only, right? Second row. Then you also print for me this one. Also, you can see here 1 by 3. All right, so this is usually 1 to 2. You can see also print for me also here 6, which is 6 here. Also print for me here 2,5, which is all rows and second columns. So that is just and matrices in Python. So you can do determinants, you can do better in matrices, you can do better. So I just give you a little explanation. I mean on that. So it's more than that. You can still go further. So we have ranges and sequences. We have a linspace, and also we have a array with range, which we have declared above before. So you see the same thing that I've just shown up above. So, but a linspace is just trying to give us a value between. We're trying to create a series of sequences now. For example, we want to create a sequence start from 0. Now the difference is that there's a difference between linspace sequence and the NP array sequence. They're not the same, okay? Linked sequence gives you the full numbers from 0 to 1. We have a step 10, all right? So that is a in decimal form, all right? So between this and this, right? But we also have for array with sequence. For this one, array with range here, which we did before, that one is give you minus it's exclusive. Okay, this one is exclusive. Okay, this one is inclusive. All right, but for linspace, all of them are inclusive. All right, so if I print this one out, I can say if I run this now, I click on run, I can have this one till 1, okay, 0 to 1. I can say stop at 1 here from 0. So this is inclusive. That this is where you can get all for linspace. Okay, but for normal array range, it does not have you all. Can you see? It can only have what you printed here. Can you see here? 0 to 8, no 10 included. So 10 is exclusive. All right, so we can concatenate array, be trying to combine two arrays together. We have a np.array, we have np.array, we have to combine together. So we can combine them together and concatenate them. So you can say we can do vertical stack, row wise, and also do horizontal stack, column wise. That's a column wise. So vertical like this, horizontal like this, column wise. So if you print out each of them, you will see difference in row wise and column wise. So if I say row stack np array a comma b, I'm trying to concatenate these two arrays together now, but I'm doing it row wise now, row wise. But I can also do it column wise. Okay, and that is how you handle such. So you can see them here. So we have what is called vertical now, column wise here, row wise rather, and then we have column wise here. All right, so we also have some. Let's look at some example now. First example, we have a data set with a rows, sample, columns. We have data array. Let's create a data array. This is data. Just created this one. Call it data, for example. So let's first normalize the data now. Normalize the data. We say mean equals to np.mean numpy. So we try to find data into axis equal to 0, just to find a normalized form. Then say we start definition as well. We should do the same thing. All right, for the data, it's our data now. Don't forget, we're trying to have each data, it's just a small data. Okay, so we can normalize now by using our normal Z form, standardize the data. So we can just pass our data formula, usual formula, data minus mean divided by std. So don't forget that formula. We have used it before in previous work. So or you can just say normalize equals to data minus np.mean data divided by np.standard. So just the same formula here applies. So you can print original data and normalize one to see the difference between the two. So this is what you do most times on a data set for machine learning. You are going to most strategy that you will bring in matrices in many dimensions, so to say. They are unnormalized. Okay, they need some kind of operations to make them usable in machine learning. So you have to perform some operation on them to normalize them, sometimes to clean them. So that is just the second concept. So but they come in this form, but very huge. So you can also apply the same method to them. It's just simple data, but sometimes you can have a very huge one in this same form. You can just apply this method, and that's you can go. Then you can continue with your what they call it now, your machine learning operation on them. So let's look at a scenario now. Let's create a scenario, for example. Now we have a scenario such question. So you are working on a computer vision project that requires the processing image data, even a grayscale image represented as a 2D numpy array. Don't forget, images actually images come in bunch of numbers. Don't forget that images they are numbers. Even though we look at them as image, or everything you are seeing there just combination of pixels, they are numbers. So don't forget that. So when we are dealing with images, we are dealing with it mathematically because they are numbers. So that is how Python handles them. So pixels normalization scale value to between 0 and 1 now to normalize now. Edge detection using a simple kernel filter. I'm going to also apply thresholding to create a binary image. So we're going to apply this on these three concepts now on this image. That is what we are asked to do. So we have to implement the pixel normalization, which means the bunch of image data you are going to be given, normalize it. That data actually is a number, but it's an image. Don't forget, I told you before that any picture you see, there are a bunch of numbers. So you can generate the numbers and just work on it, use it to predict whatever you want to predict. They are all images and numbers. Okay, so edge detection is applied to it. Then we can now apply thresholding to create a binary image. All these one are morphology-based operations. All right. Okay, so we can just import our Numpy and Matplotlib library to print out the result. So what are we doing now? We are doing image processing pipeline using Numpy array covered here. What you cover here, we have cover array creation and properties. We are doing normalization, feature scaling. We're going to do padding for convolution operations. We pad the data. We do kernel filtering, edge detection. We do Boolean indexing and thresholding, and we do vectorized operations. So this is what I'm going to see. Operation we're going to combine together here to work on this image. So this is just practically as normal data you are dealing with. So let's create a NumPy array original image. So let's assume this is our image now. This is data. Okay, this is data. This is image. Don't forget just image. So we have a NumPy array of homogeneous single data type. Shape determines array dimension 6 by 6. Okay, 1, 2, 3, 4, 5, 6. And the same thing 1, 2, 3, 4, 5, 6 by 6 array. So the types type n float 32 ensures floating point precisions. All right, so we are trying to put command edit type np.float, which means that become float 32 now. So if you run this now, it will give us this data converted to this np.float. That's the first operation. Then we have what they call pixel normalization. The data has been converted now. So go to undo the operation. So now let's use pixel. Let's now normalize the data now. So division operation is factorized now applied to all elements with critical. This is very critical for machine learning. Models converge faster with normalized input. So because when you do this model normalization, there's a fast convergence of your data when you are running machine learning. And of course, 225 is max pixels value for 8-bit and grayscale, which is 0 is smallest, 225 is highest. So we do normalize image. This we're normalizing the image now. The simple code is simply we just say original image all over 225.0. That's all. Don't forget it's down to 0.0 now because we have floated it. Okay, it's now in decimal form. That's what we have done here. So now we are normalizing it now. Just say original image, which is our data here now, divided by 225. So this is just what we do in convolutional neural network most times in a CNN. Okay, in deep learning. So when you bring images in bunch of images, I mean normal image pictures, images of data, you're trying to predict the image or classify the image. So to say, we are going to do all this operation in a simple form. Just you have to normalize them, and this is what you just do normally. So it's not a bunch of long code. Just apply just simple line of code to normalize them. All right. So you can see image padding for convolutional. Now we want to padding the image now. So add 1 pixels border around image. That's the pad 1 with pad width 1. Then constant mode fill the zeros default values required to maintain output size after filtering. So we're going to say padded image now .np.pad normalized image comma pad 1. So mode constant. So this is just what we do after the normalization. So we have to do what you call edge detection. Okay, we are going to use Sobel filters. So this is another concept in machine learning called Sobel filters when you are doing edge detection. So you what you call kernel detects horizontal or vertical edges. So the horizontal or vertical edge will be detected. So we have S over X, for example, the horizontal one. So we have a detect vertically, vertical one, edges columns. Then the over Y, Sobel Y detect horizontal edges, which is row. We have columns and row detection. So this is 3 by 3 kernels are common in image processing. So we have just call np array -1 0 1 -2 0 2 -1 0 1. So the same thing here. I call -1 -2 -1 0 0 0 1 1 2 3. So we have columns wise, we have row wise. That's what we have done here. So we are assigned them to super X and super Y. So we're going to use these two of them on our normalized data. That's what we're trying to do now. So now we can now say HSY is what mp.arrow like. We are calling this function now to handle this one. This for initial output array with some shape, same shape image as input. So we supply this our normalized for both X and Y. So we had do manual 2D convolution sliding with window operations. So for high in range, okay, in range 1 to padded image, the shape 0 to 1, so which is rows. For J also, this is columns, the same thing for columns, row and columns. Then extract 3 by 3 neighborhood. So we're going to extract 3 by 3. So window equal to padded image. This was extraction 1 minus I minus 1, I plus 2, G minus 1, so this row and columns now we are dealing with that. Then element wise collection plus sum, we have fundamental of CNN operation. Actually, this is what we do majorly in CNN. So we have edges X underscore Y, we have the columns, and we have the rows, we have the columns, these rows and columns as well, multiplying by our subel X and subel Y. Okay, so combine edge upon response using factorized operations. So edge magnitude equals to np dot square into edge, we have square of this, so this is for the X and Y, this is rows and columns. So that is done. Then we now find what they call threshold to create a binary image. Creating a binary image now is simply it's a threshold, so the 0.3, you can choose other threshold if you want. So this Boolean operation create mask true or false, S types np.unit 8 convert to zeros and ones, common in segmentation task. We are doing image segmentation. This is concept to apply. We have binary edge equals to, we can just create a binary edge, a variable now, it's called a binary edge magnitude greater than threshold dot S type unit. So you can visualize everything you have done so far. And it is our final thing we have done so far. You can now visualize what you have done so far. Then using our threshold, which is 3. Threshold can be increased, can be reduced, depending on how you want it to, or how clear you want it to be. So you can visualize the, now this is optional. So let's just okay, what we do here now, you also see image grayscale. You want to create mix now, display single channel images. We have subplot printing now, showing processing images stage by stage now, side by side. So we want to see them. So let's say we want to, let me make it a 8.4. Don't want it to be too big. Okay. Okay, so that you can see properly. That's okay. Let's say plot 8 subplot 1, 4. So we want to print the first original image now. Then we also have plot show original image in grayscale now. So we do the second one, we do the third one. Okay, this is the original one, this is normalized one. All right, so we do normalized grayscale. All right, we do edge detection with the one that have edge detection. Also we do that one. So this one we call it edge magnitude CMAP gray. So also do the one that have binary edges. All right, this is one for threshold T. Our threshold is 0.3, which you can change over there. All right, so you can print out this and see the results. We run this now. Okay, you can see original image now. This is an original image. Just assuming this is a picture that you're working with a bunch of pictures now. This is one of them. Normalize in one here, so you may not see too much difference, but machine can differentiate for you easily. Okay, so edge magnitude here, you can see. So we have binary edges T or T equal to 0.3. You can change the T to make it more distance. So you can see this is what you do in convolutional neural networks most times. Okay, so how does this apply to the machine workflow? Image processing normalization is critical for before feeding images into a neural network. You need to do all these sync processings most times. We do what they call feature extraction, edge detection, highlight importance patterns like CNN layers. We do dimensional reduction. If the dimension is too high, we reduce it. We call thresholding, simplify data while preserving structures. So we have only 3, 1, 2, 3. So that is what we do so far. So we can also apply another method by following this simple and say, okay, we work for an e-commerce company that want to segment customer based on their purchasing behavior using the Amazon sales dataset simulated performance. Perform the following: load and inspect the data set, clean missing data and outliers, calculate key metrics, average order value per customers, purchase frequency, total spending, create customer segment, high or low volume. So this is basically what we are talking about now. So we have Pandas imported, Numpy imported, and Matplotlib because we need them. Right. So here, data set is created here. We are just trying to simulate this one. Okay. I use this data, simulate it. Then we pass it our data here to df. So then we now convert the data to date and time. So this particular column here, we convert it. Okay. Then we print our initial data, the first that's the first 5 rows and columns. So we check the info. So we print it out first. Let's run the data. So this is what we have for now. The first 5, 1, 2, 3, 4, 5. So it's our data set now already. Okay, don't forget that it's our data set. So that we have already printed out. Now you can also this is our data set information about data set. Alright, so you can also do the cleansing of data, handle the missing values by first copying. If that we create a copy first, so that we not deal with the original data set, so that in case any problem happen, we can still bring it back again. So we say, okay, the clean, so df to copy, we copy the data set. So we now want to clean the data set. We'll say, okay, fill NA where there's no any data inside, fill it with this. Okay, this date and time. So that's what we do here. All right. So now we remove the negative column amounts of if there's any, if there's any at all, we remove. So we clean that off. Then we assign 0 to it. Okay. So it's okay. We do the cleaning. So printing clean data. No, where the is no, we print out also. So let's just run this and see the result. You can see in our data structure here. Now customer metrics, now we group by customer ID. Okay, you can just say, okay, we just create a statistic here on our clean group data. This is our clean data now, the group by customer ID. We do aggregation here. So total spending, amount, sum, other counting, counts, other average, mean, that is average now. So we set index, we create that. If you run, you see that here. You can see 1, 2, 3. So this is what we have created so far. So now on the same data, like I still working on the same data. Let's segment now. We create customer segmentation. So cut, create a new variable from there. It's high and low. All right. We call it label. All right. So customer statistics, total spending, our being 0 to 150 float inf. So just create a label here now. So we print segmentation now. Try to segment the data. So when we run this now, we have this one. For each customer, they will have high and low values. So far, so that's what we are doing. So if you visualize it now in a figure, you can see the output of the data we have created. So this is just a plot to see the output of the data. So if I run this line, you can see our data here. So let me see. So so this our threshold here is we use as a threshold for those who have high and those who have low. Our threshold is 150 here. So you can see from 150 upward they are high. So you can see here it is for 150 downwards low. So that is what we do here. So you can see here. So we use our Y to 150. Don't forget, this is our Y to 150. We call it red line here, segment threshold. Okay. So that is just what we did so far. So if you look at it here, we have what we have covered so far is listed here, and we have you can see the C001, C001, 0101, 0103, 104 customers. They spent higher than $150 as is high. So this target, you can target with loyalty programs now for this one. Then low value customers, only one person here, 102. Send promotional offer to increase spending. So the spending is spending too low, so we need to increase. So just adjusting, you are doing what you call customer segmentation, and that's what we do. So we have just do some introduction on the Numpy array. So in the next class we will do more, and I hope you enjoyed the class. So if you like, you can just you can like it, you can comment if you anything you want to add, or you want us to talk about. We meted, and you can also share if you want, and we continue in the next class. Thank you so much for joining. I'll see you in the next class.